Hello, Mr. Right? Okay, so remember we talked about this color map thing, yeah, color map thing. So we use the depth of search. The problem was, what was the problem? Is that we have okay, so let's review this a little bit. We have this color map, like 1, 2, 1, 2, 3, 3, 1, 1, 4. In one operation, we can change any connected piece. Look, this is connected from one color to another. And we want to find out that what's the minimum number operation in order to make all color into one single color. For example, in this case, we change 2 into 1. So let's going to take 2 operations. 3 into 1. Let's going to take 1 operation because this is connected. And 4 into 1. That would be another operation. So 1, 2, 1, 2, 3, 4. 4 operations. Okay. So how do we do it? The algorithm will be just to count the number of the islands. Yeah. Remember we talked about the island, the connected pieces, number of pieces for each color, and then we want to keep the color which has the most pieces, right? So because if we keep the color with the most pieces, then the number of operation will be the minimum, right? If we have maybe we change this to 1, okay? We change this to 1, right? We change this to 1, so this will be another connected pieces, right? So we just need the 1, 2, 3 operations to make everything into color 1. So in order to count the number of pieces for each color, then we have to store it into a data default dictionary where the keys are the colors, yeah, where the keys are the colors, and the values will be the number of the pieces. So the key thing here is that we increment this. As long as we do this depth search, we mark the connected pieces into -1 or whatever, and then we increment this color with 1 piece. So it means that we have found another piece of a connected color X, right? So we can do this with depth search, or we can do this with breadth search. So let's do it then with the breadth search. How do we usually implement the breadth search? Any idea? Come on, any people? Q, yeah, double NDQ, yeah, DQ, yeah, exactly. So we can do this, yeah. So let's remove this, yeah. We can mark it as -1, yeah. So this function means that let's perform a breadth search on pixel RC, the coordinate, with the color X. Let's do it with the color X, okay, make it easier. So with the DQ, Q equals DEQ. DEQ, what does it mean? What does DE mean? What's DE mean? Double NDQ means the Q can be we can have these operations into this is a Q double NDQ. We can have this append, pop, append left, pop left. Yeah, we can have this push and pop operation on both sides. The advantage of using this DQ is that we have these 4 operations will be the constant term operation, right? Will be constant term, okay? So if we're using a list, yeah, if we are using a simple list, this can be used as a queue, a simple queue. But the operations of using this list on the left hand side will be on constant, right? It's not on not constant. Okay, so that's why we prefer this double NDQ. Okay, so DQ, let's put the initial one, which is RC in the array. Okay, so we're using this. Okay, and then while Q is not empty, then we have to get a pixel. So current, let's write the RRCC equals Q dot pop left. Okay, Q dot pop left. Okay, can I use this please? Okay, Q dot pop left. Okay. So now we have the Q dot pop left. We get it from the Q, and then what do we need to do? We need to append its neighbors, which has 4 directions, right? 4 directions. So for DR, DC, this is offset in 4 directions. Will be 1, 0, 0, 1, -1, 0, 0, -1. Yeah, these are the 4 operations. Okay. 4 directions. 1, 0. 1, 0 means the one up under it. 0, 1. 0, 1, what does it mean? 0, 1 means on the left, minus 1, 0 on the left. This is on the right, on the left. 0, 0, 1, 0, 1 on the right, minus 1, 0 is on above it. 0, minus 1 on the left. Yeah? So now this is the offset. So the new R would be the R plus DR. And C, new C would be CC plus DC. And we have to check this coordinate if it's in range. So we can just do it. If 0 smaller than NR, bigger, smaller than rows, and right, 0 smaller than NC, smaller than columns. So if this is in range, also the new pixel is not being, it's the color we want. So it's the color. So metric. So we can only map NR NC equals color, right? If it equals color, then okay. So we Ryan, can you stop doing that? So look, if we are at RRCC, this pixel, RRCC pixel, and we want to find the 4 directions here. So in what cases we can append this pixel back into the queue? Okay, anybody?
Just back into the queue.
Yeah. So this is the pixel. We take it from the queue, and then in what conditions we need to push its neighbor back into the queue? If what? If the color, this pixel, the color is what we want, okay? And then we push in the queue, then we have to change it to map RRCC equals -1. So we mark it. So suppose this is color X, and this is also color X, right? So I push this into the queue, and I might make this -1 just to avoid this being pushed back to the queue, okay? Alright, and then Q dot append, yeah, the most important thing. Q dot append RRCC, okay? NRNC. Okay, and then we can just, and that will be, yeah, because this function we don't need to return anything. The function of the BFS function, this function would be just to say, okay, we want to mark all the connected pieces to this RC, right, with color X, yeah. Okay. So that would be the BFS search, right? That would be BFS search. We can just plug in, replace this with the BFS search, and all should continue to work. Okay. Okay. So any questions so far? I mean, guys, this is a BFS search. The color. So let's give an example. Okay. Just to review a little bit. Okay. 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 1, okay, 3, 1, 2, 2, 1, okay? So which color we want to keep, obviously?
1, 2.
No, okay, let's just go through the algorithm to see if which color we want to keep. No, you're not connected as okay. So this is not connected. Okay, I'm going to let's go through the algorithm. Okay, so we have a dictionary data. Yeah, we have a dictionary data. Data is here. Come on, data. Okay. Okay, I'm starting at 1. Okay, and then I want to mark all the connected pieces using depth search or breadth search here. Right. So that will be 1, 1, 1 here. I will change it to all -1, -1. So now 1 have 3. 1 has 1, okay? 1 connected. And then we skip the -1. 2, the connected pieces here, right? 2 and then 1 pieces. And we need to make it as -1, just to avoid being visited again. 3, only 1 pixel, -1. 1 here, -1. So we increment this 1 to 2, right? 3, -1, that will be and edit another one. So 2, right? And 1, make it -1, 3, 3. Okay, 2, make it -1, increment 1, 2. 1, make it -1, increment 1, 4. Okay, so now Eric, right? Look, color 1, we have 4 pieces of connected. Number 2, we have 2 connected. Number 3, we have 2 connected. So which color we should keep? Which color we should keep from here? The key is that color. The values will be the number of 1 exactly. So we keep this one. So the number operation will be 2 plus 2. Yeah. So actually we sum up the value will be 4 plus 2 plus 2, and we get the maximum 4. So 4 plus 4. 4 plus 2 plus 2 minus 4 equals what? 4 plus 2 plus 2. This is the sum minus the maximum 4. Which is the answer? So what's the 4 exactly? That will be the answer. Okay. Yeah. Okay. So that will be it. Okay. That will be it for today. Yeah. Thank you. Bye bye.
Bye.
Bye bye.